Welcome back to Applied Mathematics. In this video, I want to talk about propagation of error, which is probably the most important idea behind significant figure analysis. We've seen previously that we can use significant figures as a way of describing how an approximate value is approximated using vocabulary of the accuracy, number of significant figures, and precision, the place value of the last digit, the place to which it was measured or to which it was rounded if it's a calculated value. In this video, I want to talk about what happens if you have a calculation involving several approximate values. How do you determine the accuracy and the precision of the resulting value based on the accuracy and precision of the measurements that went into the calculation in the first place? Let me get my head out of the way, and I'm going to start with a fairly silly example. I think it makes a lot of sense to look at an extreme case where we know what the answer is and we know what makes sense as the answer, and then we'll try to analyze how we can make that work. Consider a room which measures 153.6 inches by 107.9 inches, approximately 12 feet by 9 feet. I want to take this room and apply wallpaper. Various wallpapers are various thicknesses, but let's go with a wallpaper that is 0.003 inches thick. That's fairly average for the thickness of a wallpaper. What are the dimensions of the room after we apply the wallpaper? Well, before we get into this, it's not going to change, right? The thickness of wallpaper is not going to affect our measurement of the room. But in theory, we could calculate this. We could take the 153.6 inches across the room. We could subtract the 0.003 inches that we lose on the left wall and subtract the 0.003 inches we lose on the right wall. If we do that, we end up with 153.594 inches. And when you look at that measurement, you realize it's really not that different from what we started with, which is what we expected. And in fact, if you think about it, we can even take that a step further, because the difference between 153.6 and 153.594 is a more precise difference than what most tape measures are capable of measuring. Right? When we write 153.6, that tells us that the precision of our measurement, well, we know it's in inches, so it's probably going to be an eighth of an inch or a 16th of an inch. A 32nd of an inch would give us one more significant figure, but somewhere in that range, eighth of an inch or 16th of an inch is pretty close to a tenth of an inch. And if we're using a tape measure that is only marked to the nearest 16th of an inch, we can't see any difference between this measurement and that measurement. It's the same number. And so that is kind of the result that we're looking for. I don't want this to be a different number. I want to say that I'm going to try to measure it with my tape measure that's only going to give me to about a tenth of an inch. I don't know what's going on with the video over there. Sorry about that. Anyway, I want this to be to within the nearest tenth of an inch. So I'm going to round my result to the nearest tenth of an inch. When I do that, because this is such a ludicrous example, I'm not that surprised that I get the same measurement that I had to start, 153.6. Now I want to try to codify that and get us something a little bit more careful. So let me get my head out of the way and get a little bit more room to write. The precision rule tells us that when we are adding or subtracting approximate values, we should round the result to match the worst precision among the original measurements. So if we consider something like 4.58 plus 7.72. This is actually fairly typical of addition and subtraction. Not all of the time, but most of the time, values that you are adding or subtracting are going to come from the same measuring tool, and so they will have the same precision. In this case, both of these values are precise to the nearest hundredth, 0.01. So when we add them, it doesn't matter which one is better or worse, they're the same. All right, so if I grab out my calculator and I punch in 4.58 plus 7.72, my calculator gives me 12.3. I like this example because it's actually the opposite of what usually happens. But in this case, when I wrote that result, I only have precision to the nearest tenths place, not the nearest hundredths place like I had in the original measurements. So in fact, I have to introduce one more digit in order to match up that place value. So 12.30 is precise to the nearest hundredth, the same precision that we had before. The interesting thing in this case is that we started with two measurements that had 3 significant figures, and we ended with a measurement that has 4 significant figures. The accuracy does not matter at all when you're adding or subtracting, only the precision. These numbers were rounded to the nearest hundredths place. I wrote my result rounded to the nearest hundredths place. Let's take a look at another example. 43, I guess. I was going to write a different number, but my hand wanted to write 43.258, so we'll go with that. And then let's subtract 9.61. This is an interesting case because the two numbers have different precisions. They also have different accuracies, but we don't care about accuracy when we're adding or subtracting. 43.258 is precise to the nearest thousandth. 9.61 is precise only to the nearest hundredth. So if I jump back to my calculator, and I punch that in, it gives me 33.648, but I'm going to round that to the nearest hundredths place and call it 33.65. Right, 64, but the next digit is an 8, which tells us to round up. All right, so this is, again, to the nearest hundredths place, the worst of the precisions of the original two measurements. An interesting thing that happens in this problem, if you look at the two original measurements, we have a 5-digit accuracy and a 3-significant digit accuracy. The result came out as a 4-significant digit accuracy, which I think is useful in showing that the accuracy in addition and subtraction has absolutely no bearing on the result. The only thing that matters is the precision. When you are trying to do any other operation, the rules change. So let's go ahead and take a look at the other rule of approximate values. Which is called the accuracy rule. The accuracy rule tells us that when we are multiplying, dividing, evaluating an exact exponent, or evaluating a root, we should round the result to match the worst accuracy of the original measurements. I do want to stress here this rule only works when we have an exact exponent. So let's start with that example. If we have an approximate value, like 3.785, and we raise it to an exact exponent, like 3, then this rule will work. If we tried to use an approximate exponent here, like 3.72, we would have to use a completely different rule that's beyond the scope of this course. So as long as that remains exact, we're in good shape. And so let me grab my calculator here, and let's calculate 3.785, the whole thing raised to the third power. My calculator gives me this value, 54.22476,163. That's quite a mouthful. But we can round it using the accuracy rule. Our initial measurement here has 4 significant figures. So I'm going to take just the first 4 significant figures of this result. 54.22. One of the things I want you to notice is that the original measurement was to the nearest thousandth, and the result comes out to the nearest hundredth. The precision of the values can and will change. The accuracy stays the same, and that's the thing that's important here. That is going to hold true for any of the 4 operations. I'll leave the calculator on screen here and just run through a couple real quick. All right, how about a square root of, I don't know, 73.825? I notice that 73.825 has 5 significant figures. So when I take the square root of 73.825, my calculator gives me this long string of digits. I only take the first 5. 8.5921. There's 5 digits. The next digit is a 4, tells us to round down, so we're in good shape. If we are multiplying, then all of a sudden we have 2 approximate values to worry about, and then we have to go through a lot of the same considerations that we went through working with addition and subtraction. And unlike with addition and subtraction, having different numbers of significant digits is very common in multiplication and division, because they usually are going to be different kinds of measurements that have different kinds of units. For example, we might have a time, like 7.3 hours, that we're multiplying by a speed, something like 48.0 meters per second. Notice in this measurement, let's give me a little bit more space to draw some arrows. The first value here, 7.3, has 2 significant figures. The second value, 48.0, has 3 significant figures. Between them, the worst case scenario is having 2 significant figures, so that's what we're going to use as our rounded result. I'm going to take 7.3, I'm going to multiply by 48.0, My calculator gives me 350.4. I want just the first two values. Conveniently, remember the 0 at the end of a number is not significant if the number does not have a decimal point. So only the 3 and the 5 are significant here. We have two significant values. The other thing that I want to point out with this one is where the precision happened. And this is a place where if I had units written down in the problem, I think it would make a little bit more sense, but we'll talk a lot more about how to deal with units in calculations a little bit later. I said that maybe this 7.3 was a measure of time. It's in hours. So the precision there was to the nearest tenth of an hour. I said that this 48 was a speed. It was maybe in miles per hour. So my precision there is to the nearest tenth of a mile per hour. And when I multiplied these things together, the result is going to come out in miles. Again, we'll talk later on in the course about how to figure that out. If you're not comfortable with that part of the calculation, you don't need to be yet. But the key here is the precision here is in the tens place. Tens of miles. But miles, miles per hour, and hours are three different kinds of measurements. Comparing the precisions between them doesn't really make sense. And that's another key reason that we don't use the precision rule. That's why we stick with accuracy. That's why we care about the number of significant figures. The worst case among the two numbers we multiplied together was two significant figures. So we took a result and we wrote it with two significant figures. All right. One last rule that I have to talk about. I guess I could do a division problem, but it's all the same, so I think you've seen enough examples here. An exact value has infinitely many significant figures and is infinitely precise. This is a long way into why we write our exact values as fractions instead of as decimals. So if I have something like 3/7, if I try to put in 3/7 in my calculator, it just tells me it's 3/7. If I tell it I want a decimal approximation, it gives me this, 0.428571429. But my calculator has to stop at that point because it is only capable of displaying 9 significant digits. The 3 and the 7 have infinitely many significant digits. And so writing it as a decimal approximation, we lose accuracy. Since we don't want to lose accuracy, we leave it as 3/7. Likewise, I might write a square root as, that's supposed to be a 5, the square root of 5 instead of trying to get my calculator to give me the approximate value. Because the square root of 5 as an exact value, is infinitely many significant figures. 2.236067978 has, I think, 9 significant figures if I counted that right, maybe 10. But we've lost infinitely many significant figures, so we don't want to write that out. If I'm trying to do things with an exact value and an approximate value at the same time, well, then I have lost things. So if I have something like 23.9 and I want to multiply it by the square root of 5, I can punch 23.9 times the square root of 5 into my calculator, and my calculator automatically says, oh, you want an approximate value. Because over here, we have 3 sig figs. Over here, we have infinitely many sig figs. The worst case is the 3 sig figs, so I have to take that result and round it to 3 significant figures and call it 53.4. This is an idea that you have already seen in our previous discussion, because unit conversion factors are all exact values. If I have 7,500 feet and I want to multiply that by 1 mile over 5,280 feet, well, over here I have something that has 2 sig figs. And then over here, I have a conversion factor. Conversion factors are exact. So that has infinitely many sig figs. When I punch it into my calculator, I get this horrible decimal approximation. The worst case scenario is this 2 sig figs. I write it as 1.4 miles. Right? So I guess the one question that's left is, how do you know whether you have an exact value or an approximate value? We've talked about that a little bit previously. If you are the one taking the measurement, then it should become very apparent. If you measured something using an approximation tool, like a ruler, or calipers, or a micrometer, then your result is an approximation, and you know the precision of your approximation, and you can use that in your calculation. If you measured something by counting, then it is an exact value. If you didn't count or measure, and you looked up a definition, like 1 mile is exactly 5,280 feet, then that is an exact value. If it's written using a square root, it probably is an exact value. If it's written using a fraction, it probably is an exact value. But a lot of the context is going to be very dependent on you trying to figure it out, right? And for very simple problems like we're going to be looking at right now, where by and large I'm going to leave the units out and I'm just going to give you, here, do this calculation, you're going to have to rely a lot on the instructions, right? So if I gave you this problem, I would specify the decimal numbers are approximate, the whole numbers are exact. And then you can work it out from there. Right. I think that that's enough. This is going to feel a little bit strange at first, and as I've mentioned previously, this is not the one and only rule for working with significant figures, but it is a fairly common one. And if you can master a rule, you can master any rule. I will mention very briefly one of my favorite rules, and when I teach physics courses, I tend to rely on this rule very heavily. Every measurement I give you is going to have 3 significant figures, round it to match. I want you to learn how to adapt to significant figures in this course, so we're not going to use that simplification this semester, but I just wanted to mention one more time before we wrapped up that these sorts of simplifications are fairly common. But I think that's far enough for this video, so thank you as always for joining me, and I'll see you next time.